Okay, as we've seen, for any simple harmonic oscillator, F net equals negative Kx, where x is displacement from equilibrium. Now, if I have, say, this rubber band, and at this length, it's just ready to start exerting force. It exerts a little force here, but I relax that just a little, and now it's exerting no force. Now, if this rubber band is, in fact, linear in the force configuration, in the force response to being stretched, in other words, the force is a linear proportionality to the distance from the position at which the rubber band exerts zero force, then if I stretch this out some distance x, I'm going to have a force F equals negative Kx trying to pull it back. So as I stretch from here to here, the force goes from 0 up to negative Kx. Of course, I'm moving in this direction, and the force is in this direction, so that the force exerted by the rubber band is going to be in the direction opposite our motion, so that the work done is going to be negative. Now, how much work is done in stretching the rubber band from position 0 to position x? Remember that at x equals 0, that's the position at which you get zero force, okay? Stretching from position 0 to position x, our force goes linearly with respect to x from 0 up to negative Kx, so that our net average force is going to be 0 plus negative Kx over 2. And that's just, because 0 plus negative Kx is just negative Kx, that's going to be negative Kx over 2. Okay, so the net average force is negative Kx over 2. Now, how much work is done? Okay, how far have we moved? We've moved distance x, or we've moved through a displacement x. Okay, and the rubber band force, the elastic force, is exerting force negative Kx in that direction. Average force is negative Kx over 2. Distance is x. So how much work is it? Well, we multiply our net average force by delta S, and we get negative Kx over 2 multiplied by x. X is our displacement, delta S. That's going to give us negative 1/2 Kx squared. That's the work done by the elastic force. Okay, now, assuming that we have a situation where that force is conservative, and with the rubber band the force really isn't conservative, but with a good spring, for example, the force would be very nearly conservative. So if you have a conservative net force, in the ideal case, that's what you have. You get the change in potential energy is what? It's equal and opposite to the work done by the conservative force. Here's the work done by that net force, which is conservative in the ideal case. So you're going to be equal and opposite to that negative 1/2 Kx squared, giving you a potential energy change of 1/2 Kx squared. So when the rubber band stretches from here to here, now it's got a potential energy of 1/2 Kx squared. Now, I'm using a rubber band. Rubber bands aren't really conservative, so this would only be an approximation to the potential energy that you actually have with the rubber band. If I had a good steel spring, then this would be a much better approximation. The potential energy would be much closer to 1/2 Kx squared. Remember, for a rubber band, we don't even really have a constant K. The F net versus X is not quite linear, although this gives us a pretty good approximation in many cases. Okay, so the whole point here now is we go from x equals 0 to position x. Force goes from 0 to negative Kx. Average force negative Kx over 2. So the work done by the net force is negative 1/2 Kx squared. In the ideal case, F net is a conservative force, so the change in potential energy is equal and opposite to that. So the potential energy at position x is 1/2 Kx squared. Now, one thing you absolutely need to know is the potential energy at position x is 1/2 Kx squared. You should also understand how that was obtained, but bottom line, be sure you really know this. You should know where it comes from so you won't forget it. Okay, so you'll know how to use it also, so you can make similar arguments in other cases.